By the end of this lesson, we will be able to interpret graphs of piecewise linear functions. A piecewise linear function is a graph of lines that may be broken up into different pieces. So let's get started. For our first example, we want to examine the difference between distance as time changes. So for our first bullet, it says a graph moves upward when distance from the starting point increases. So let's take a look. The time is 0, the distance is 0, meaning whatever object this is has not moved yet. And as time goes on, if the graph is moving upward, it's indicating that the distance is increasing. Whatever object this is moving further away from its starting point. So second, we have a graph that moves downward, and comparing distance versus time, is actually decreasing, meaning that it's moving closer to its starting point. So as time goes on here, now its distance is going down, indicating that it must be getting closer to where it started. Next, we want to interpret the horizontal line, this segment right here in the middle. This means that as time is going on, the distance appears to not be going up or down. So we can say that there is no change in distance. Whatever object this is must be remaining in the same place. Now the final bullet here wants to describe the steepness or the slope of the line. So the steeper the line, you want to realize that the faster the change in distance. So here, if this is an example of a car, let's say at time 0 the car is at home, and as time goes by, this person is commuting to work and they take a few hours to drive to work. So as time is increasing, as hours pass, the distance the car travels away from home increases. Now this blue section could be that the car remains in a parking lot while the person is at work. So the distance is not changing. It's not getting any further away from home, and it's not moving any closer to home. And then finally, this car is going to return home. Now notice the green line is steeper than the red line. The person may have traveled faster to get to work, and it may have taken longer to return home, possibly because of traffic. Okay, now let's examine the difference between elevation or height versus time. So, first example indicates that as the graph moves upward again, that would indicate when the height is increasing or rising. As the graph moves downward, that would show that the height or elevation must be decreasing or lowering. Again, we have another horizontal line segment. So this horizontal line indicates that there must be no change in height. As time is moving on, the height of this object is not changing. It's not getting higher, and it's not getting lower. And then the steepness of the line is similar to before. The steepness of the line is telling us that there is a faster change in height for that period of time. And so for this example, maybe this is describing the water level inside of a container. At first, the water level is rising, and then for a period of time, the water level remains the same, and then the water level is decreasing, it is draining. The green segment and the red segment here appear to have a very similar steepness to them. One's just positive, one's negative, but the slope seems to be similar. So maybe that's indicating that the rate of change is similar. One is not necessarily happening faster than the other. Although if I had to choose, maybe the green line is a little bit steeper. Okay, our third example wants to compare speed versus time. This one can be a little confusing. Let's start with, as the graph moves upward this time, that would be on this piece, again, it indicates when the speed is increasing again, or speeding up. Now when the graph moves downward, I should say downward, let's correct that. Which changes to downward. So when the graph moves downward, at this first segment and this last segment, it's indicating the speed is decreasing, or some object must be slowing down. horizontal line segment here and here is indicating that there is no change in speed. That means that the object must still be moving, but just traveling at the same speed. Constant, not speeding up or slowing down. And now the steepness of the line. So the steeper the line, the faster the object is speeding up or slowing down. Okay, so an example we could use for this one is a car again. Let's say a car is traveling. Here, at time 0, it appears that the car is traveling at this specific speed. But now, as time goes on, it appears that the speed is decreasing, meaning that the driver could be hitting the brakes or slowing down. And then here does not mean that the car is stopped. It means that it's traveling at a constant speed, the same speed. It's not. It's not hitting gas or increasing its speed, and it's not hitting the brake, slowing down. Okay, so now we have a green segment. So now the person must be pushing the gas and increasing the speed of the car. And then again, it remains at the same speed for a little while, and then it starts to decrease again. So let's say maybe the car was initially traveling at about, let's say 50 miles per hour. So now they hit the brakes and now until they're down to about 30 miles per hour. So they're going to stay at 30 miles per hour for a little while. Then they're going to hit the gas and maybe travel at 40 miles per hour. It's going to take them a little while to get there, and then they'll stay 40 miles per hour. They're not going back to their original speed of 50, but they're getting closer. And then again, they start to hit the brake and slow the car down. Okay, let's interpret the following graph by answering the questions below. At 11 o'clock, Lizzie's mother sends her to the corner store for milk and tells her to be back in 30 minutes. So she's supposed to be back in 30 minutes. Let's examine the graph to the right. First question wants to know how long is the entire trip. First, it's important to notice that this is the time at the bottom on the x-axis, given in minutes, and that the y-axis is describing the distance away from home in meters. So we want to calculate how long the entire trip was. Well, time 0 is here. Time 0 indicates that she had a distance of 0. So this is when she's at home. Okay. Now, she's not at home. She's traveling further and further away. She's traveling further away. She's kind of the same distance for a little bit. And then she's getting closer to home, closer to home, closer to home, and she returns back home here. So the entire trip lasted 40 minutes. So if the entire trip lasted 40 minutes, next we want to know at what time did she arrive home. Well, she left the house at 11 o'clock. This would indicate that she arrives home at 11:40. Why was her mother upset? Well, if we recall, her mother instructed her to be back in 30 minutes. So she was late. So she was upset because Lizzie should have been back by 11:30. Lizzie was late. Lizzie was late. Okay, so now how far away from home was Lizzie after 12 minutes? Let's take a look at the graph for this. So after 12 minutes. Minutes are at the bottom, so let's find 12 minutes, and then let's follow that up to the graph to find the distance she was away from home. So now point C represents time 12 minutes from when she left the house. If I look across, it tells me that 12 minutes later, from when she left her house, she was 400 meters away from home. Okay, for part D, we want to know when does Lizzie arrive at the store. So now, let's think about this. It's getting further away from home, further away from home. Oh, it's actually asking how do we know when she's at the store? Getting further away from home, and then something stands out. D and E are the only 2 points that remain at the same distance as time continues to change. So as time is going on, Lizzie is not changing her distance away from home. This must be when she was looking for milk. So when Lizzie's distance remains the same, she must be at the store. Now the question is, when did she arrive? When did she arrive at the store? Well, D is the beginning time for when she gets there. Let's follow that down and indicate that She arrives at the store 16 minutes after she left, which would be at 11:16. Okay, now we're asked how long was Lizzie at the store for? So let's take a look, and it shows that she's in the store from B until E. So let's follow this down, and we see that she's in the store from 16 minutes till 20 minutes. That's a difference of 4 minutes from point B to point E. The next question was now how far away is the store from Lizzie's home? How far away? So the store is up here. This would tell us about the time, so let's look across to the y-axis. The entire time she's at the store, she remains 600 meters away from her house, so the store is 600 meters away from home. Okay, part D wants to know, was Lizzie's trip longer going to the store or coming back? So let's separate this into two pieces. Going to the store. So going to the store, she leaves her house here, she's still traveling, now she's at the store. Let's figure out how long that took, which we mentioned before. It took about 16 minutes. So from point A to D, she's traveling to the store, which took about 16 minutes. Now let's check how long it takes for her to travel back. So she leaves the store at point B, and she's traveling, gets to home at point G. So point B, let's see what time that is. She left the store with a 20-minute walk. And then point G, she returns home with a 40-minute walk. So let's start off with from point B to point G, so travels back. And we're going to need to find the difference between the 40 minutes total that it took for her trip and then the first 20 minutes of traveling there and picking up the milk. So it indicates that coming home took 20 minutes. So it turns out that coming back certainly took longer, by about 4 minutes. Okay, part H wants to know why is line segment FG, so FG here, how is this line segment steeper than line segment EF? So I'm actually going to erase all of these highlight marks so we can take another look. So we want to compare EF to FG. Why is it steeper? Well, it indicates that it's traveling faster. Lizzie was traveling faster during FG than EF. But why? Why was she traveling faster? Well, that's right, she was late. So she may have been trying to rush, knowing that she was already late. Here, at F, it's 20 minutes. She only has 2 minutes to get home, so maybe she increased her speed so she could get home on time. Unfortunately, she did not make that. So now tonight's video lesson should help us practice tomorrow in class. We want you to be able to practice interpreting graphs of these linear functions. Thank you for watching.